So our first speaker is Andy Strominger, and as our custom is, his formal talk will be about 40 minutes, and then there's 10 minutes for discussion. And so I'll tell you when you have 10 minutes left, if that's good with you.
Okay,
and he's
great.
going to use
So
the blackboard. So.
Okay, great.
You probably must.
Are there also blackboard lights?
Yeah, there are blackboard lights, believe it or not.
So first of all, happy birthday, Jeff. I've known Jeff for a very long time. And we have written, well, according to my Inspire page, I've written 15 papers with him, but according to his, he's written 14 with me. So there's some kind of an anomaly there, which I will leave as a topic of future investigation. But those papers were written on many different subjects over a period of 10 years, from 1985 to 1995. I think that they laid major parts of the foundation for what happened in 1995, and certainly Jeff has been an incredible intellectual as well as a good friend. We had many life events happening at the same time, and yeah, he's been a very important person in my life, and we are still talking about a problem with M24 and black holes, and one of my goals in life is to beat Greg Moore, who has written 17 papers with Jeff. So happy birthday, Jeff.
Wait, 17 is what Jeff's page says. What is Greg?
This was not the archive, this was Inspire. So I'm going to talk about a paper I wrote rather recently called The Universe as a Quantum Encoder. I wrote it with a new junior fellow, Jordan Kotler, who mostly works on quantum computers and quantum information, but he has a huge wave function, a small fraction of time he spends on black holes and quantum gravity, and I got a little piece of that. And so this paper was a lot of fun, and I thought would be of interest to a general audience like this. We were talking yesterday about how these are people from all of Jeff's life and all of his academic life, and everybody changes their fields. And so now all of us at one time were in a very close field to Jeff, but now we represent a huge swath of physics, and it's been to me to be really nice to be at a conference like this where there are talks that everybody seems to be able to be getting something out of. Okay, so we start with the following, what I have long felt to be kind of a white elephant in the room of theoretical physics that everybody was ignoring. And that is that the following three facts are, contradiction is too strong a word, but they're certainly in extreme tension. One is that quantum states on different time slices are related by unitary transformations. Psi of t prime is equal to some unitary transformation, t prime t, psi of t. The second is that the universe is expanding. And the third is that there don't exist any degrees of freedom on distances less than the Planck scale. That is, there's a fundamental shortest distance scale in nature, which we might think of as kind of a lattice at the Planck scale, and that you can't talk about degrees of freedom, new degrees of freedom ever emerging as you go farther and further into the UV, as one does in ordinary quantum field theory. Quantum gravity, it should stop at the Planck scale. And if it didn't, it's hard to imagine how there could be a consistent story of black hole entropy. So why are these in conflict with one another? Well, if the universe is expanding and there aren't any degrees of freedom on the number of Planck scale, then the number of degrees of freedom has to be increasing, and you can't have a unitary transformation between two Hilbert space with different, the dimension of the Hilbert space is roughly the number of degrees of freedom, and you cannot have a unitary transformation between two Hilbert spaces which have different dimensions. And this has been noted and remarked on in various different places. I'll quote one in a minute. And so that's one way of thinking about it. So there's another way of thinking about that where you get this tension. One is the same as one, two things which are in contradiction with each other. And two is that there's a Big Bang. And there's no ekpyrotic pre-universe. So this is an even more extreme version of it, because you can't, if there's a Big Bang, it means that there's a time before which there was nothing, and you can't have a unitary transformation from nothing to something. So both of these seem to present a big problem for theoretical physics. And I would mention that this first one comes up and has been discussed in the context of black hole evaporation, where it's not the whole universe that's expanding, and it's just the region outside, the light rays expanding outside the horizon, and it's related to the fact that the Hawking quanta which come out were super Planckian before the above any Planckian cutoff, if you sort of trace them back in time to where they would have been had they been present at some very early time. Okay, so in this,
the universe, the Hilbert space could be infinite dimensional, so I don't understand this argument. Infinite.
that's why I very carefully use the word tension.
So,
No, that doesn't prevent the third, that doesn't prevent the last one. And indeed, this second one has led us into all kinds of contradictions. That's why I use the word tension, not contradiction. Yeah.
in the theory of gravity, you have Hamilton in zero. I mean, are you including, are you quantizing gravity? You have to impose a constraint.
Yeah, this is certainly gravity, yeah.
But then there is, okay, I don't know. Total Hamiltonian is zero.
Okay,
Right?
you're free to think of things the way out of it. I use the word tension, not contradiction.
Okay.
And I'm using my words very carefully. Now, the difference between these two is that in this one, we never have to talk. This kind of problem is, encountered in, measurements of the cosmic microwave background. It's encountered in black hole evaporation. It's encountered in a weakly coupled context. This only happens in order to talk about this contradiction. You're forced to talk about the Big Bang, where quantum gravity becomes strongly coupled, and then we know less what to say. So in this paper, we propose the idea that we give up the sacrosanct God of unitarity, and we propose the idea that time evolution is not unitary, but it's something called an isometry. And there are many kinds of isometries, and they're sort of the main thing that are studied in quantum information theory. And they are maps from smaller Hilbert spaces to bigger Hilbert spaces. And of course, that's exactly what you do when you build a quantum error correcting code. You start out with some small Hilbert space code subspace, and then you add in some more degrees of freedom, and you get some bigger entangled state. And the way that this can happen, there's a lot of very beautiful mathematics, which I learned from Jordan, about this. And it seems to apply, we think, quite well to this context. Now, what is it? What is an isometry? Well, suppose we have psi I. Let's take a bigger Hilbert space, sort of I greater than alpha. So we have some transformation, psi I is equal to pi alpha psi alpha. So alpha is the smaller Hilbert space, and P is the bigger Hilbert space. I is the bigger Hilbert space. This cannot possibly be unitary because it's not an n by n matrix. This is, say this runs over m greater than n values. However, we can demand that P alpha I, Pi beta is equal to delta alpha beta. That is, if you evolve a step forward and then come back, you get back to where you started from. And moreover, that Pi alpha, P alpha j is equal to some projection, Pij. If you go backwards, you get some kind of, you get a projection. Okay, so the hypothesis that we're going to make is that in quantum gravity, not in quantum field theory, but in quantum gravity, we should more generally talk about isometries rather than universes. Now, and of course, in isometry, it becomes unitary as soon as the sizes of the two Hilbert spaces are the same.
Are some stars here?
Yeah, maybe we want some stars. Okay, so now this has been, I'd like to remind you of some discussions that went back in the early 90s. And there's a very nice, a lot of people talked about what do we do about the fact that these slices outside the black hole horizon are expanding in any way that you describe them, with a cutoff or with a lattice, especially in these 2D models where it could all be very explicit. You ended up having something where there are more degrees of freedom. And why wasn't this a problem? And this is, of course, closely related to the fact that the outgoing Hawking radiation, which many people have complained about, if you evolve them backwards in time, become super Planckian and would have been above any exponentially super Planckian and would have been above any reasonable cutoff. So the words that were said, that sounded very good to me at the time, but probably I said them myself, many people were saying them, is that the new degrees of freedom as the universe expands don't introduce any uncertainty because they come in their ground state. Now, so the picture that I think one had in mind when one heard that was a lattice, and that as you expand the universe, you keep the lattice, the Planck length, and you add new points, but at the new point, the thing is in the ground state. But that's clearly wrong because a single degree of freedom, if you add it and you put it in its own individual ground state, that's a highly excited state. That means it has no correlations with any of its neighbors. So if a new degrees of freedom come in, it had better be correlated in just the right way with all its neighbors. You can't just add a new lattice site and say that that thing is in its ground state. That takes a lot of energy. So probably a Planckian amount of energy if it's a Planckian lattice. So the idea is that an isometry is just a rule for specifying what the quantum correlations are of the new degrees of freedom that we need to add as we move along. Now, I just want to say that, so there are different kinds of isometries. There's some with some very beautiful mathematical properties that have come out called quantum error correcting codes. Those can be, they're also closely related, and we'll see this isn't an accident, they're closely related to renormalization group flow. When you're integrating out degrees of freedom, you're sort of doing a reverse isometry, but if you integrate up a renormalization group flow, you have to add new degrees of freedom, and you explicitly use an isometry, which in many cases is either a quantum error correcting code or close to a quantum error correcting code. And there's a whole literature about that, and that will be related to what I'm saying here, because in DS-CFT, time evolution is a renormalization group flow, and so this idea that would it be an isometry gives it a lot more teeth.
This also reminds me a little bit of your work on non-commutative solitons, where you had operators that obeyed U dagger U as one, but U dagger was not the identity. Those are partial isometries.
You'll have to remind me about that word. Let's not let
That was the one paper. But now we found it.
But yeah, there have been touches of non-commutative geometry come in here, definitely. So this is just some words, but I think we actually backed it up in 3 different ways, of which I'll probably only have. So I didn't know whether to call this a conjecture or a argument or a demonstration, so I went fishing around in the dictionary, and I found the word hypothesis, which I think I should have discovered earlier in my career. So
There's something called the scientific method.
you can't disagree. A hypothesis can't be wrong. A hypothesis is an idea that you're putting on the table with some evidence, but not overwhelming. You're not asserting that it's true, but you think it's worth studying, and you have some you have some support. You're not just something you pulled out of a hat. You have some supporting things. So
You're also allowed to conjecture that something is a hypothesis.
okay, so we did 2 things. The most compelling of one I find, that's a calculation I did some time ago, is the continuum analysis of a moving mirror, something which everyone will be able to follow. I think shows that even in the crazy simple example of 1 + 1 dimensions in a moving mirror, that we should think of time-free field theory, that there's a sense in which it's really an isometry. The second is we put it on a lattice, and it's totally obvious on a lattice that if you're adding more lattice points, that you can't have a unitary transformation, and we showed explicitly that if you use the finite element methods, you get isometries mapping the Hilbert space at a Lorentzian lattice. You get isometries mapping the Hilbert space at one point to another point. And the third thing was a little more involved. We took this very beautiful work on the radial evolution in anti-de Sitter space. There's a quantum error code by Dong, Liu, and Harlow Elmeri, Preskel, okay, Yoshida, the one other person I'm missing, who show that radial evolution in de Sitter space is a quantum error correcting code. It's too strong. They had a toy model in which it was a quantum error correcting code. And if you take that and you put a de Sitter brane world, that radial evolution becomes time evolution, and you get a quantum, you actually get an isometry, which is quantum error correcting for code for time evolution in de Sitter space. So let me start with the moving mirror. So just in 1 + 1 dimensions, and we have ds squared is minus dt plus dt minus. And what I want to do is I want to take a mirror at rest, then I want to uniformly accelerate for some finite period of time, and then I want to just stop accelerating. And of course, it goes up to scribe plus, and we get a Penrose diagram that looks like this. And this problem, I think, is solved in Burrell and Davies. There's certainly 1,000 papers on it. And you get some radiation. Inertial detectors skating along scribe plus will detect some radiation. And just to be, during the acceleration, and just to be specific, this boundary, if I let this be t plus and this be t minus, sorry, this is the metric, this is the metric in t plus t minus coordinates, but the boundary is not straight. It's t plus equals t tilde minus, where t tilde minus is equal to t minus for, say, negative t minus. For t minus less than 0, that would be here. And then at some other, I let it accelerate up to L, and during that region, it's equal to 1 over kappa 1 minus e to the minus kappa t minus. This is for 0 less than t minus less than L. And then after that, I just let it be e to the, just to make it continuous, it's e to the minus kappa L t minus minus L 1 over kappa plus 1 over kappa 1 minus e to the minus kappa L. Yeah, that's for t minus greater than L. So this is free field theory, and it's not in Burrell and Davies, but eventually what we want to do is we want to consider a state on scribe minus. So we would think there's a pure state on scribe plus. We would think there's a pure state on scribe plus. And we can divide it at any point, say t minus, trace over what's left, and we can define an entanglement entropy. And there's a formula that was for this entanglement entropy, which is that S entanglement, this was worked out by Holte and Wilczek in flat space, and Fiola, Preskel, Trivedi, and I in the curved space case a few years later. And it says that the entanglement entropy is the central charge, which would be 1 for a free scalar, divided by 6 times rho of t minus, where rho of t minus, rho is, there's no conformal factor there, but these are also not inertial coordinate, these are not inertial coordinates sorry. Rho is the conformal factor in the t tilde minus coordinates, which are the coordinates in which the quantum field is normal ordered. Okay, so this is the usual thing. And so I would like everybody, so now let's draw a graph of S entanglement and T minus. And I would like everybody just to think for 30 seconds about how they expect that graph to look. So of course we have two important points. We have 0 and we have L. And here's what's happened. First of all, it's very important that S entanglement is not a number. It's ultraviolet divergent. It also has IR divergences, but they aren't so important in this. They're related, but they're not really so important in this problem. So in fact, there's a sense in which it's immediately infinity because of short distance vacuum entanglements across any point. But we assume that we have a detector that has some finite cutoff, and that cutoff can be way, it can be the Planck scale, it can be way above any of the quanta that we see here, and that we can just normalize S entanglement so that it's 0 down here when we're just sitting there in the vacuum. It is in fact easy to see that it's constant as a function of time T minus, so we have to do a subtraction. And then during this period.
Oh, Andy, are you actually really looking at a relative entanglement entropy?
No. I'm just looking at trace rollover out. I mean, you could phrase the subtraction in that way, probably. Yeah, you could phrase the subtraction constant as subtracting off what the entropy would have been if we hadn't altered the metric. And then it rises in exactly the way, this is in fact been discussed as a model for black hole evaporation. It's got some thermal temperature and it rises. How does it rise exactly? It goes like, it goes like, the energy flux is C times pi times T Hawking, which is the surface acceleration over 2 pi over 12 times T minus. And no, sorry, the flux is just that. It does that for amount of time L. And then you might think, okay, this is a pure state. Obviously, it's going to come back down. But it doesn't. It just stays there forever. So any observer will conclude that information has been lost. Any observer with any finite cutoff will conclude that information has been lost in this insanely simple example. Now, how can we understand that conceptually? Here's how we can understand it. Let's look at early times. So we imagine that we have the same kind of detector up here, or emitter down here, and detector up here. If we have a quantum that goes here and comes back here, its frequency and some coordinates will be the same. But if a late time quantum will be redshifted because the late time mirror, though stationary, is Doppler shifted relative to the early time one. And therefore, since our real Hilbert space has a cutoff in it, there's more degrees of freedom in the final Hilbert space than the initial Hilbert space, because stuff that was above the cutoff coming in got redshifted down to below the cutoff. And those of you who've studied black hole evaporation will understand that this is exactly what happens. You have the super Planckian modes, and these are also the things that we observe, in CFB. I mean, some of that stuff at early times in inflation is insanely above the Planck scale. So the Hilbert space is bigger here. And since the Hilbert space is bigger, we really can't talk about, well, we can if we want, I guess. I mean, I think we could set this up in such a way that it looked unitary, but it's more natural to think of it as a Hilbert space or it seems to me it's more natural to think of it as a Hilbert space that's changing size. And so if even in this simple example, we can see that Hilbert spaces want to change size, especially if we're going to talk about measurable entanglement entropy, why should we be insisting on exact unitarity as a exact statement about every situation we ever encounter? That's what prompted us. Now, we can also do this in cosmology. We can easily do it in 1+1 dimensional cosmology. And there we can write ds squared equals minus r squared of t dt plus dt minus. And so now we can imagine a cosmology. For example, we could consider something like this, where we let it be static for a while, and then we let it expand for a while, and then we let it be static again. And again, if you take the universe, say, and divide it in half, here, and you keep that division line, and you measure the entanglement entropy of the two halves of the universe, you'll find that it's increased by amount which is c/3. If we call this c/3 log r plus infinity over log r minus infinity. So even these continuum results suggest to us that we should think of the number of degrees of freedom, that there's more degrees of freedom up here than down here, but we have to add them in a careful way. And we seem to vaguely understand how it is that we do that, but it's not by unitary transformation. It's really more by an isometry. And we can also do this in de Sitter space. And in de Sitter space, well, let me talk about that in a second. I'll talk about that a little bit later. Okay, I'm going to just talk about the lattice just for a minute or two.
We got about 10 minutes in the formal part.
Okay. Are there any questions about that before I go to the lattice? Yes.
Yeah, so you could have picked any slicing in the case of moving mirror, and there would be some sort of a Hamiltonian evolution from one slice to another. But what part of the Hamiltonian that moves the mirror, that moves the boundary conditions, must be non-unitary, right? Whereas in the de Sitter story, it's a bit different.
When you say Hamiltonian, you need a space-like slice. So my answer to the question is going to depend highly on what kind of space-like slice you're talking about.
Any foliation, I guess, that
Is it going to end on scry, or is it going to end on?
eventually, at late time, I guess I want to.
Well, those are, of course, are not. There is not unitary evolution because stuff leaks out in between.
But is that because there's a boundary condition that's moving and there is no Hamiltonian that moves the boundary condition, or is it?
Well, it's just because slices which end at scribe plus are not complete.
Oh, fair enough, okay. But you say there's no difference between expanding universe and a moving boundary condition, because there's no quantum gravity here, right? It's just field theory statement.
Well, I feel quantum gravity is important in the conceptual, because in field theory, we do seem to formally be able to discuss UV fixed points that are conformally invariant and they have degrees of freedom and infinitely many degrees of freedom and arbitrarily short distances. That seems to be a consistent thing to say. And I wouldn't want to, and you wouldn't want to think about it this way. But I feel that in quantum gravity, you're going to be hard pressed when you're in more complicated curved space. I mean, I don't know, yeah, with more complicated curved space situations, to have a rule that is always exactly unitary. The most famous of them, of course, is the Big Bang. How are we going to have a unitary explanation of the Big Bang? And you really need quantum gravity to have a Big Bang. Yeah.
At least for the case with the 1 + 1 EDS, how do you square this off with the Wheeler-Dewitt equation expectation that the wave function would just sit and not evolve at all?
Well, I think that there's a sense in which if you take a series of slices like this, then you'll have unitary evolution along those slices.
If you take if you take the Cauchy surface to be all of scribe plus, are you saying that the state on scribe plus is not pure? Or I think I'm missing the.
I'm saying that if you measure the purity of the state on scribe plus with any real detector, you will conclude that it is not pure, no matter how long you wait. You'll be waiting for those page quanta to come back and you'll never see them.
So you're saying the infrared modes are the key to why it's not pure. Like it's really if you cut off at some like time.
That's not what I'm saying. I'm saying it's not unitary, it's isometric. That it's better to think of it as isometric. There aren't some mysterious long wavelength modes
Yeah, that's what.
that I'm ignoring here.
But you're just doing quantum mechanics with a time-dependent Hamiltonian.
That's right. So
So why is that non-unitary? It's just explicitly time-dependent. So yes.
I told you the sense in which it's non-unitary, that an observer who measures the quantum state at scribe plus and has a finite cutoff, no matter how large, will conclude that the state is mixed.
Is there can you actually exhibit an isometry that does this for these observers, that acts on the Hilbert space in the way that you want? Or not on the Hilbert space, but maps a smaller Hilbert space to a bigger Hilbert space? I mean, you've kind of said that's the right language, but you've argued to think that way, but can you actually?
We can very explicitly in de Sitter space.
Not in this moving mirror problem.
We haven't, but it would be certainly interesting to, but what we did, we did it on a lattice, but there's something not satisfying about what we did. There's a long section which is pretty technical on a lattice, and there's been a lot of work on lattices and curved space and so on. And you have to use something called the finite elements method rather than the finite difference method on curved space, and we did that, and we found that we exhibited the isometry. We wrote a formula for the isometry. We latticized the thing. We wrote a formula for the isometry. What we did not do, but seems within the realm of possibility, is reproduce this formula from that isometry. But it's clear that all we did was we took and latticized this in the most obvious way. Well, maybe I'll just say one word. Here's our moving mirror, and the finite difference method would tell you to lattice it like this. And then have a boundary. Now we do this. And then you have a boundary that sort of looks like this. And that's nasty because even in the continuum limit, your boundary becomes a sawtooth, and in the continuum limit, you're injecting a Planckian amount of energy into the system if you scatter off the boundary. So that's not what people do. What people do instead is they triangulate, and then you do this and this, and you have some way so that the boundary becomes smooth in the continuum limit. And we did that, and we worked out the isometry, and you could look at it with formula, and isometry, but we did not reproduce the formula, which would be a great thing to do. But in principle, it seems like it should be possible.
I think, all these calculations in 2 dimensions you can get from anomalies, right, basically, which you can view from as an infrared conformal anomaly, right?
Of course, that's where Philip Breslow and I got that.
Anomalies you can always view from an infrared perspective and not from, I mean, if you look at it from the perspective of anomalies, it's not, why do you have this Transplanckian problem?
Well, I think the infrared picture is that the late time boundary is redshifted relative to the early time boundary.
But then you don't have to talk about Transplanckian energy. If you think of it in terms of anomalies.
We don't have Transplanckian energies here because our shift is just a finite factor. We don't have an exponentially growing factor like you do in the black hole, around outside a black hole.
Yeah, but my question is that since anomaly calculation, you can always formulate in a low energy theory.
We have a free theory.
But yeah, okay, yeah.
So I'm running out of time. So I said my statement about the lattice. And now let me just say the one other thing that we did to substantiate this point of view was we took the this very beautiful sort of tensor network construction of of ADS by Dong, Harlow, and Almeri, yeah, Dong, and also by Harlow, Preskill, and Yoshida, and they had a story where an excitation here, you could write it as you considered an excitation at the origin, and as you moved radially in the origin, you found that the state at subsequent radii was, the Hilbert space gets bigger because the number of degrees of freedom in the description of this excitation at different radius depends on the number of edges you cross. So they were doing an isometry, which in fact they showed was a quantum error correcting code, very specific one. And it gave a holographic representation of the quantum state all the way out at the boundary. And then I combined that. So that's a very beautiful thing, I think. Then I combined that with a paper I wrote with Hawking and Moldacina about 20 years ago, in which we considered a brain world embedding of de Sitter space and ADS. And the effective theory on the brain world is a CFT coupled to gravity. And And so then you can, so then this radial evolution, since the radius is increasing, in the expanding part of de Sitter space becomes time evolution. So in this, the induced time evolution on this brane world from the Harlow and friends is in fact not just an isometry, but a quantum error correcting code. I know I'm out of time, but I'm just want to say one word about DSCFT. So in DSCFT, the idea is that you start with a CFT. This would be the inflationary patch. You start with a CFT at the boundary, it's scribe plus. And this is inverse RG flow. Sort of ADS on its side. And as you, if you were to deform this CFT by a marginal operator, you would reach a trivial fixed point. So it would just kind of end, and that would give you a Big Bang story, like in the Klebanov-Strassler thing, where you add a marginal operator to n equals 4 Yang-Mills and ADS, and the space just caps off. So this is sort of Klebanov-Strassler on its side. That would be Big Bang cosmology. And in that story, I talked about this as RG flow, and I talked about taking the correlation functions and calculating them during RG flow. I never discussed states, but this isometry story gives a very nice way of talking about states on sequences of slices. And indeed, there's a whole literature relating RG flow to quantum error correction. And so they fit. And that, of course, fits into the Harlow et al. Picture that we're used to radial flow and ADS as being RG flow, but there's also a connection between RG flow and quantum error correction. So let me just stop there.
Okay, time for questions. Yes.
So in the moving mirror story, you had a UV cutoff, correct?
Yeah.
And have you thought at all what would happen if the UV cutoff were near a UV fixed point?
It's a free field theory. It doesn't flow, so it's at a fixed point. It's a formula which applies to any CFT.
Oh boy, we've got a lot of questions. Lance and then Paul and then over here.
So this is far from what you talked about, but it kind of reminds me of these ideas that calculating the vacuum energy and interpreting that as a cosmological constant in the standard way sort of isn't right, because you're not counting the number of modes in the volume. They should be on the boundary. And here you're sort of, I think, saying there are fewer degrees of freedom somehow, or at least, you know, you're not sampling them in the same way because of not having the unitary evolution. Is there anything to that, or is that?
Yeah, there's a point of view that yeah, I think it should affect some of those discussions. I also think it should affect probability discussions in the multiverse, which is not my thing. But Jordan likes to talk about the way to think of it, the way you think of it with quantum error correction. You know, if we think of an expanding universe, you start out with a code subspace. You start out with a code, and then you keep adding more stuff into it, but you want to correlate it so that you can, you know, you have this complicated message and you can decode it. Now, if you restrict to the code subspace, the code subspace is unitary. Evolution in the code subspace is unitary. So there's something unitary in this problem. You keep adding junk. The problem is, if we go to the moving mirror problem, I mean, I think that's a completely valid point of view. If you go to the moving mirror problem, if you try to figure out what the code subspace is here, it's non-locally spread out. It evolves in time. So it's entangled. It's true that there is some degrees of freedom that involve unitarity. There's unitarily, and then there's all the other ones that are just add-ons to hide the code. But any real measuring device would, you can't build a measuring device to only measure stuff in the code subspace. I don't know if that, but yeah, closest thing I could say to your question, yeah.
Well, we still have a question.
Actually, a follow-up to that, and going back to what you said in the beginning, you talked about how when you're expanding universe, you add lattice points, and formerly you've been naive, those were in the ground state, but of course they're not correlated, so that would be high energy. And what I'm trying to get intuition for, since I'm familiar with
Incidentally, just let me stop you there. There's one thing. So Joe, those words are from various people in the early 90s wrote reviews of the black hole. Those are from Joe's thing. And he actually has the phrase in there, the system is one-way unitarity, which is probably what I'm saying here, because what is one-way unitarity?
Yeah, and of course, I mean, the notion of having to be correlated plays a large role in the later firewall paradox. But the thing I'm trying to get intuition for being, so I'm familiar with stabilizer codes. I know how that mapping into the code space works. But I was hoping to get some intuition for, because I can't see it in a finite dimensional system of where I've got this mapping into a code space and I start adding more points, and can you see explicitly how that mapping permits you to come back and tell you to what state to put what the nature of the correlations of those added points have to be in order to maintain my same position in the code space. That's what I'm having trouble getting intuition for.
Well, okay, so two things. I mean, that's a very example dependent question. So that question would have a very precise answer in my third example, where you embed into we just sort of lifted all the results out of the happy paper and the Arlo paper and so on, and added the DS World Brain. And there's a very special, we use the hexagon, single bit hexagon code for one state. They give all and it's an isometry with it's isometry, which is a quantum error correcting code, which is sort of the best way to store the information. It's the most impervious to being destroyed by measurement. And so you could answer it in questions like that, but I don't know about in general. Yeah, but that's a very good question. And is it a question that could be made precise in this moving mirror example? That would be a great thing to do. Let me just add, I forgot my concluding questions. My concluding questions is it obvious if we give up on unitarity that black hole evaporation, loss of information is a problem? I think yes. No, it's not obvious, but I think this must be taken into account. And if you think about it, my gut feeling is that this is not the essence of the black hole information problem, but we should understand. And indeed, in these simple models that Jeff and I worked out 1 million years ago, we saw that there was a change in the in the entropy at some finite retarded time, and there also is here. And we're not throwing this out. Nobody's suggesting another way to do this calculation, and it's entirely plausible that maybe those models make sense in this way. I don't think it solves the whole problem, but I don't know. I think we need to think about it. And the other thing, which nobody's asked, but maybe somebody is about to ask, is what if the universe is contracting rather than expanding? Like inside a black hole or in a big crunch. And that brings in a whole new can of worms, because when the universe is expanding, you go from low energy effective field theory to lower energy effective field theory. And if it's contracting, you go from low energy effective field theory to high energy effective field theory, where you don't know what's going on. And so we just said, we don't know what to say about this. It's an interesting question. It did arise where high energy is understood in the ADS problem. And they have a statement about it there, which makes a lot of sense. It's about the degeneracy of black holes that sit in there and so on. And yeah, so I don't know how to think about it in general. We're not making any statements about that. It's a big open problem. Both of these are big open problems.
You just answered my first question, so I'll ask the second one. These maps look similar to, or they remind me of the Hawking dollar sign matrix ideas. Are these related at all, or? These identities look similar is what I'm thinking about, but at the top.
Yeah. Well, it's not quite the one. Yeah, I don't know. I mean, I think the Hawking, eventually that became more specific, and as it became more specific, it became clearly wrong.
Yeah, no, it just, yeah, the original idea, not the applications or something, but I think the formalism at the start seems kind of similar.
Might be.
Yes.
You're putting a cutoff on the system. I mean, with the mirror, wouldn't it be consistent to assume that the mirror can only like reflect modes below some frequency? I mean, in which case some of those modes would just travel through, and there would be, you wouldn't have the unitary evolution just from that point of view. So I mean, you're putting sort of a cutoff in some places, but not others. That seems a bit confusing.
Well, that is what we're doing. Yeah, that is what we're doing. We're using these calculations. I'm not the one who calculated this, right? This thing was calculated before I was in graduate school. I think that though many things were calculated having to do with moving mirrors and so on, I think the usual assumption would be that you have an exact Dirichlet or Neumann boundary condition at a mirror, and then you compute the radiation, compute the quantum state that reflects off that, and then you try to measure it, or you compute that. You compute the entanglement entropy. People wouldn't usually talk about it in detector. They say compute that, and there's an infinity, and you just throw the infinity away. I don't see anything conceptually inconsistent about assuming that it's an exact reflecting boundary condition along this trajectory. It's well-defined.
I mean, there's some weird things. For example, it requires an infinite force to do that. And there's some like, you'd be like the radiation reaction on the mirror. It's infinite unless you put in a cutoff and so on. So
Right.
Or a physical mirror wouldn't. Well, if you're trying to model some physical system, which I thought was the idea here, then.
Well, let me say it this way. we just compute this. Exactly. We assume this all exists exactly, free field theory with Dirichlet boundary conditions with it. We can certainly write down all the formulas for this. And then we compute, instead of computing the S entanglement here, we compute D minus of S entanglement. The derivative along here. So we drop the constant. We set it equal to 0, and we look at the change in entanglement entropy from back here. And database this curve. And then I never have to say the words finite cutoff.
Okay, let's thank Andy. We're gonna be on coffee break.
Yeah.
Until, actually, what was it, 11:20?
Back to the rituals.
So we've got plenty of time to continue. And remember Jeff's students, was I your student? I can't remember. We're gonna gather with him for a picture.